Welcome. Myself, Dr. Praveen Purohit, Department of Chemistry, Engineering College, Bikaner. Today, we will be discussing about bomb calorimetry, that is, determination of calorific value of solid and liquid fuels. Calorimetry. Now, this name is familiar to each and every student of science, and calorimetry itself is derived from the Latin word calor, meaning heat, and the Greek word metry, meaning to measure. It is the science of measuring the amount of heat, and it is an integral part of thermochemistry. Technique that we use to measure the amount of heat involved in a chemical or physical process is known as calorimetry. Calorimetry is basically used to measure the amount of heat which is either transferred to the system or it is taken out from a substance. A calorimeter is a device which is used to measure the amount of heat involved in a chemical or a physical process. Both the process, that is chemical and physical, may involve heat exchange, and it is measured with the help of this instrument called as calorimeter. The most common example of a calorimeter is a coffee cup calorimeter. As shown in the diagram, we can see that this is actually a double-walled coffee cup calorimeter, and the simpler version can be reprinted like this. Here you can see that a double wall is present so as to prevent the loss of heat due to radiation. The system is dissolved in water, is placed here, a thermometer is placed here, and it is covered with a lid so the rise or the change in temperature is measured. Now this is basically used mostly by the simpler chemical reactions. The general chemistry students often use simple calorimeter constructed from polystyrene cups, and these easy to use coffee cup calorimeters actually allow more heat exchange with the surrounding, and therefore they produce less accurate energy values. So enthalpy of reaction, the internal energy change of the reaction, or any kind of the energy changes taking place during a chemical process can be carried out in an approximate manner using a coffee cup calorimeter. Now, scientists actually use much advanced instrument for measurement of the heat exchange, and that is actually a bomb calorimeter. In the diagram, it can be seen that it has an adiabatic wall, which is actually an insulator to the heat. The system itself is closed. It has a thermometer, a mechanical stirrer. A system is placed here where the chemical or any kind of the combustion process takes place, and the heat exchange takes place. And as a result of this, the water gets heated up. So scientists use these well-insulated calorimeter that all but prevent the transfer of heat between the calorimeter and the environment. This enables the accurate determination of the heat involved in a chemical process, the energy content of the foods, and so on. The use of an adiabatic bomb calorimeter basically eliminates the losses to the surrounding, and the result is more accurate heating values as compared to the simple coffee cup calorimeter. Now, when we are using a bomb calorimeter, since the system is totally closed, so the bomb calorimeter is actually a constant volume calorimeter. So constant volume, that is an isochoric process is carried out. It should be noted that since the experiment is at constant volume rather than constant pressure, the change in internal energy, that is V is equal to constant, is being measured rather than change in the enthalpy, where P is kept constant. Now, to convert from change in internal energy to the change in enthalpy, it requires knowing the amount of work done during the reaction, and these are interrelated by the equation delta H equal to delta U plus delta N gases RT, where delta Ng gases stands for the change in number of moles of the gaseous reactants and products. Now, units of heat. When we are performing calorimetry, we should have an idea about what are the various units in which the heat is actually observed or measured. Calorie. It is the amount of heat required to raise the temperature of 1 gram water by 1 degree centigrade. That is from 15 to 16 degree centigrade. So 1 calorie is equal to 4.185 joules, which is equal to 4.185 into 10 raised to the power 7 ergs. Kilocalorie. It is the amount of heat required to raise the temperature of 1 kg of water by 1 degree centigrade, 15 to 16 degrees centigrade. It is a bigger unit than calorie and therefore is related to calorie as 1 kilocalorie is equal to 1000 calorie. Then British thermal unit or BTU, amount of heat required to raise the temperature of 1 pound, that is 1 lb or libra water by 1 degree Fahrenheit, 60 to 61 degree Fahrenheit. The relationship between BTU calorie and joules is 1 BTU is equal to 252 calories, 0.252 kilocalories, 1054.6 joules, and 1 kilocalorie is 3.968 BTU. There is another unit called as centigrade heat unit, that is CHU, which is amount of heat required to raise the temperature of 1 pound, that is 1 lb or libra water by 1 degree centigrade, 15 to 16 degrees centigrade. 1 kilocalorie is equal to 3.968 BTU, equal to 2.2 CHU. These were actually the various units in which the heat is calculated or calculated. Now, the heat given per unit volume, per unit mass, known as calorific value, can be calculated, and there exists a relationship between the different units of the calorific value. These relationships are for solids and liquids. Since the calorific value is expressed as per unit mass, it is given as 1 calorie per gram is equal to 1 kilocalorie per kg of the substance and 1.8 BTU per lb. And for gaseous fuel, since it is per unit volume, so 1 kilocalorie per meter cube is equal to 0.1077 British thermal unit per cubic feet. Also, 1 BTU per cubic feet is equal to 9.3 kilocalorie per meter cube. So this is how different calorific units are related. Now the calorific value itself is of two types. As it can be seen, it is of higher calorific value and another is lower calorific value. As the name indicates, higher calorific value, it refers to a higher value of calorific value. It is the amount of heat produced when a unit quantity of fuel is burnt completely and the products of combustion are cooled to room temperature. So, mostly all types of fuel which contain hydrogen results in combination of the hydrogen, and the hydrogen presence during the combustion is converted into steam. As the products of combustion are cooled down to room temperature, the steam gets condensed into water, and the latent heat of condensation of steam also gets included in the measured heat. The calorific value thus measured includes the latent heat of condensation and is thus higher and is called higher or gross calorific value. As depicted in the simple diagram, we have a closed system heating a mass, unit mass of the substance M, and it gives Q amount of heat as a result of the combustion process. And at the same time, the water vapor, steam, etc., are not allowed to pass, and they just condense, giving out Q1 amount of heat as the heat of condensation. So the total amount of heat observed is Q1 plus Q2 divided by M, which is HCV. LCV, or the net calorific value, it is actually total amount of heat produced when a unit quantity of fuel is burned completely and the product of combustion are not allowed to cool down to room temperature. So what happens is the product are permitted to escape out, and that is the water vapors and moisture etc. are not condensed and escape out with hot combustion gases. Hence, the latent heat of condensation of steam is not added and the value is lower and is called as the lower calorific value, which is called as the low calorific value or the net calorific value. Simple diagram represents here is an open system involving burning of a mass of a substance. It gives only Q amount of the heat as the heat of the combustion, and the escaping gases and water vapors actually just pass out, and so the calorific value Q by M has a lower value as compared to HCV. There exists a relationship between the HCV and LCV. So it is given, we know that HCV is greater than LCV, and LCV can be calculated as HCV minus 0.09 into H into 587 calories per gram, where this H is actually the percentage hydrogen present in the fuel. LCV stands for the lower calorific value, HCV stands for the higher calorific value, H is the percentage of hydrogen in the fuel, and 587, it is the latent heat of condensation of the steam. So by using the above formula, the LCV HCV are related. Now, the relationship can be calculated out as, let the percentage of hydrogen in the fuel is given as H. According to the chemical equation, the water produced is given by H2 plus half O2 gives H2O. On weight basis or mass basis, we can write as 2 grams of hydrogen gives 18 grams of water. So we can see that 1 gram of hydrogen actually gives 9 grams of water. So since we are taking percentage of the hydrogen, so we consider 100 gram of fuel will contain 8 grams of hydrogen, and 1 gram of the fuel will contain H upon 100 grams of hydrogen. Now, suppose 1 gram of the fuel produces 9 into H by 100 grams of water. Then latent heat of condensation of steam of this much amount of water produced by 1 gram of the fuel will be 587 into zero point zero 0.09 into H into 587 calorie per gram. So LCV can be calculated as HCV minus this latent heat of water form, that is 0.09 into H into 587 calories per gram. Now we will discuss about the instrument which is used to calculate the calorific value of a solid and a liquid fuel. As the name indicates, bomb calorimeter. It is a type of, as we have discussed earlier, a constant volume calorimeter which is used in measuring the heat of combustion of a particular reaction. Now, bomb calorimeter have to withstand the large pressure within the calorimeter. Actually, when the substance is burned inside the stainless steel vessel, a very high pressure is produced, and as a result, the reaction is being measured at a very high pressure. So, this is the reason for such a name, that is bomb word is actually used. Electrical energy is used to ignite the fuel. As the fuel is burning, it heats up the surrounding air. It will also heat up the water outside the bomb, and the change in the temperature of the water allows for calculating the calorie content of the fuel. This is actually the basic uh, principle on which the bomb calorimeter is based. So it can be summarized as a known mass of the solid or liquid fuel is burnt, and the amount of heat liberated is absorbed by a known mass of water and is measured. From this, quantity of the heat produced by burning a unit mass of fuel is thus actually determined. Heat gained is equal to heat loss. The basic principle is used in the bomb calorimeter. The heat gained by water is equal to the heat lost by the burning fuel. If we look at a bomb calorimeter, the simple diagram represents a bomb calorimeter. Here we can see that the bomb calorimeter consists of these four parts as shown in the diagram. See, the first part, it is actually the sample. The sample, the solid or the liquid, when it is a liquid paste or the liquid in a particular starch or some other substance is actually used, and a known weight of the sample is actually placed inside this bomb calorimeter, and then the second is actually the oxygen. Now, and it is burned inside the bomb, and it is airtight, and so oxygen is supplied here, and it is maintained at a particular pressure, and then only ignition can take place. And then these sample and oxygen both are present. The sample and oxygen both are present inside this stainless steel bomb. It itself is submerged in water, which gets heated up by the chemical reaction taking place, the heat exchange taking place during the chemical reaction. Now, the process of ignition is carried out by an ignition switch, which is present here, and the Beckman temperature thermometer measures the rise in temperature. If we look at an assembly of the bomb calorimeter, it looks like this. It consists of a stirrer, the calorimeter, the ignition unit, and the pressure gauge is present, which actually measures the pressure. And the pelletizer or the pellet is actually made of the paste of the substance that is actually used. So this is what an assembly of a bomb calorimeter which we are using in our lab. It is a much more closer view of this. It has a digital window which actually indicates the rise in temperature before ignition and after ignition. Now we'll discuss each part of the bomb calorimeter. A stainless steel bomb. The stainless steel bomb looks somewhat like this, and we can more elaborate it in this figure. We can see that this part consists of two inlets. Valve here is there, and this valve is connected with this. So for the oxygen supply, these two inlets are for the electrodes. The electrodes are submerged like this, and the electrodes at the base actually One of the electrode has an ring attached to it in which the crucible is placed where that fuel is actually placed. Now the entire assembly can be represented: the vessel of the bomb, the screw over this, it is placed here, and then the screw it is tightened up, and the magnesium ribbon, etc. They have been placed here in this ring, and the crucible sample is placed. So this part represents actually here the inlet, and here you can see that this particular point is here. So the stainless steel bomb, it is a container made up of stainless steel. On the top, it is provided with a lid or gas tight screw cap. The lid is provided with two holes for electrodes, and in the middle, one oxygen inlet valve necessary for ignition. One of the electrode is provided with a ring by which a nickel or silica or the stainless steel crucible can be attached, and the crucible contains the given sample of fuel whose calorific value is to be determined. A magnesium or platinum fused wire touches the sample present in the crucible. It is only with the burning of this magnesium wire that the ignition process takes place. It can be clearly seen that this is for the oxygen inlet, these two are for the electrodes, and they are electrically connected to the ignition unit. And these electrodes, the electrode has a ring, and the crucible containing the sample is attached to it. Then comes the copper calorimeter. The bomb is placed inside a copper calorimeter containing a known amount of water. The copper calorimeter contains a thermometer called Beckman's thermometer, which is very sensitive and records 1/100th of a degree. A rise in temperature can be measured easily. It has an electrically operated stirrer. Calorimeter at its bottom has two stands which support the stainless steel bomb, and it can be seen in the diagram. This is actually the stirrer, electrically operated. The sample placed inside the bomb, the water inside the bomb, inside this copper calorimeter, electrically operated stirrer, and then the temperature recorder or the water. And digitally, the temperature is recorded with the help of this Beckman thermometer, and the magnesium wire is actually used for igniting through this ignition box containing an ignition switch. So rise and decrease in the temperature can be measured easily. So air jacket and water jacket are present in order to prevent the heat loss during the process of radiation. As it can be seen in this diagram, this is the air jacket and this is the water jacket. So any kind of the rise in temperature of the water is actually this air jacket, water jacket acts as an insulator, and therefore what happens is only the temperature rise of the water is measured with the help of this Beckman temperature thermometer, and during the entire process, the electrically operated stirrer is kept on so that the uniform heating is being carried out. Now, working. A known mass of the fuel is taken into the crucible. The crucible is supported over the ring. The lid of the bomb is then tightly screwed, and then the bomb is filled with oxygen at about 25 atmospheric pressure. Bomb is then lowered down into the copper calorimeter containing a known mass of water. The electrically operated stirrer is switched on and initial temperature of the water is noted. The electrodes are then connected to a 6-volt battery and the circuit is completed. As soon as the circuit is completed, the ignition takes place, sample starts burning, the heat is liberated, which is absorbed by known mass of water. Final temperature is then recorded. During the entire process, the stirring is continuously done so that a uniform temperature is maintained. Now, based on this observation, calculation is carried out. Let us burn X grams of the fuel sample in the crucible. Now, when it is burned, then the W gram is the mass of the water taken in the calorimeter. Small w gram is the water equivalent to the calorimeter, stirrer, thermometer, bomb, etc. T1 degree centigrade is the initial temperature of the water. T2 degree centigrade is the final temperature of the water. C calories per gram is equal to HCV, or gross calorific value of the fuel. Heat liberated on burning the X grams of the fuel is equal to weight of the fuel burned into the calorific value. So X gram into C calories per gram. Heat absorbed by the water Q equal to M into S into T, given as W into S into rise in temperature T2 minus T1 calorie. Now where S is the specific heat of the water, 1 calorie per gram. So on substituting the value of S equal to 1, the heat absorbed by water is given by W into T2 minus T1 calorie. Now also the heat absorbed by the apparatus is equal to the water equivalent of the apparatus into T2 minus T1 calories. So the total heat absorbed by water, apparatus, etc. will be given by W T2 minus T1 calories plus W T2 minus T1 calories. So it can be collectively written as heat liberated on burning X grams of fuel is equal to X gram into C calories, and the heat absorbed by water is equal to W T2 minus T1 plus small w T2 minus T1, which is equating the two heat liberated is equal to heat absorbed. So it can be written as X grams into C calories is equal to W, taking common T2 minus T1 here. So W T2 minus T1 calories. So it is actually the HCV or calorific value can be calculated as W plus W T2 minus T1 divided by X grams of the fuel taken. So this expression is actually used for calculating the higher calorific value or simply written as C. So this is the way how to calculate the calorific value or the higher calorific value. Now also their LCV can also be calculated. Let percentage of hydrogen in the fuel is equal to H. Then again, weight of the water produced by this percentage of hydrogen, H2 plus half O2 gives H2O, 2 grams gives 18 grams of water, so 1 gram gives 9 grams of water. So we can see that 100 gram fuel contain H grams of the hydrogen. So 1 gram fuel contain H by 100 gram of the hydrogen. So 1 gram of fuel will produce 9 into H into 100 grams of water. And if the latent heat of condensation steam is equal to 587 calories per gram, then actually the latent heat of water formed is 0.09 into H into 587, and therefore HCV is related to LCV as LCV is equal to HCV minus 0.09 into H into 587 calories per gram. Now, this was all about calculation of the calorific value, but there are some corrections also which has to be incorporated for calculating the final value of the calorific value. The fuse wire correction. Fuse wire correction, it is the heat liberated or produced in the calculation of the calorific value. It includes the heat given out by the ignition of the fuse wire also. Therefore, it must be subtracted from the total value and is called as the fuse wire correction. Acid correction. Now, since the fuel contains nitrogen sulfur, the sulfur and nitrogen are oxidized under high temperature and pressure of the ignition into nitric and sulfuric acid, as can be seen by the chemical equation that H plus H2 plus 2O2 gives H2SO4 plus heat, and then N2, it should be N plus H2 plus 3O2 gives 2HNO3 plus heat. So it can be seen that these two are the exothermic reaction. So the measured heat also includes the heat given out during acid formation. It must also be subtracted from the total value. Then cooling correction. Cooling correction is actually the time taken to cool the water in calorimeter from maximum temperature to room temperature, and it is noted from the rate of cooling, that is dt by per minute, and the actual time taken for cooling, that is t minutes. Cooling correction of dt plus t is calculated and added to rise in temperature. So based on this, the HCV and LCV are calculated as W plus small w T2 minus T1 plus cooling correction minus acid correction plus fuse wire correction divided by weight of the fuel that is actually burned. So this actually gives the correct value of the HCV, and the LCV can be calculated by using this correct value of HCV as LCV is equal to HCV minus 0.09 into H into 587 calories per gram. There is a theoretical formula also for calculating the calorific value of a fuel if the constituent percentage is given. Now see, if we have the constituent as carbon, hydrogen and sulfur, and the higher calorific value of carbon is 8080 calories per gram, that of hydrogen it is 34500 calories per gram, sulfur 2240 calories per gram. Then the Dulong formula, he derived a formula as 1 by 100 8080 carbon plus 34500 bracket H minus 0 by 8 plus 2240 into S kilocalorie per kg or calories per gram. See here, we are using 1 by 100 as we are considering the percentage of carbon, hydrogen, oxygen, sulfur in the given fuel. 8080 refers to the HCV of carbon, 34500 as calorific value of hydrogen and the sulfur here. Now, the factor H minus O by 8 is very important for calculating the calorific value. See, H is represent the percentage of these elements respectively. The oxygen in the fuel is assumed to be in combination with hydrogen, that is fixed hydrogen, and is only extra surplus hydrogen supplies the necessary heat. This is the important thing, and the concept of fixed hydrogen can be understood like this: amount of hydrogen available for combustion is actually total mass of hydrogen in the fuel minus fixed hydrogen. Now, what is this fixed hydrogen? Fixed hydrogen is nothing but it is 1/8 the mass of oxygen in the fuel. How do we derive this? Let us consider the equation H2 plus half O2 gives H2O. On weight basis, it can be seen that 2 grams hydrogen combines with 16 grams of water, oxygen to form 18 grams of water. So 1 gram of hydrogen will combine with 8 grams. It can be reversely said as if 8 gram of oxygen is present in the fuel, it will combine with 1 gram of hydrogen to produce 9 grams of water. So if O, that is O% of hydrogen, oxygen is present, then it will combine with 1 by 8 into O grams of hydrogen. So you can see that the O grams of oxygen is present in the fuel, then the amount of hydrogen combined to form water is given by 1 by 8 into O. And therefore, with the help of this, the fixed hydrogen, this is actually the fixed hydrogen, and we can calculate the amount of hydrogen available for the combustion. So this was about the Dulong's formula. This was all about the Dulong's formula, how to calculate the calorific value theoretically. So with this, I think this lecture was sufficient enough to explain the bomb calorimeter